So this video is going to be a discussion about 8-bit PWM as it applies to our MC9S12XDP512 PWM module. And when we generate waveforms with this PWM module, they're going to be square waves, and typically you will know something about the frequency or period of the waveform you're trying to generate. So we generally want to start there. And first of all, I think I'm going to go over a little bit of an explanation of how the PWM module operates and how it generates the waveform. And then we can work backwards through the math to figure out how we'd configure the module to give you the waveform that you're looking for. So remember, we are creating square waves, so typically these things will start high and then go low after a certain amount of time. And when we're doing this, this is actually considered positive polarity. And unless we say otherwise, usually we're talking about positive polarity. So waveform starts high, after a period of time it will go low. And then with our PWM module, this will repeat. So we'll go and generate another one of these waveforms and so forth. So this will continue on. So we're looking at one period of this is what we're trying to set up. And that is, of course, how we describe this. This would be the period, as it always is for a waveform, and in the case of positive polarity, this would be the duty. So the high time, basically, of that waveform. And the PWM module isn't really all that sophisticated. It's actually pretty straightforward. The duty and period that we plug into our registers, DTY and PRD, I think is what they're called, these are in 8-bit counts. And they are counts, actually, of the clock that the PWM module is running at, and we'll get into that in a bit. But these are just 8-bit values when we're doing 8-bit PWM. And obviously they're 16-bit values when we're doing 16-bit PWM, but we'll do that under a separate cover. Okay, so all the module does is it literally counts the number of duty counts and then turns the wave on high for that part. And then when it reaches that count, it puts the output waveform low, and then continues to count until it reaches period. So if we make a real basic example of this, say we make the duty 4 and the period 10, the entire waveform is going to be 10 counts, and the duty, so the positive time of the waveform, would be 4 counts. So if we were to sort of divide this up, that would be 0, 1, 2, 3, 4, and then we'd continue on 5, 6, 7, 8, 9, 10. So all the module is doing is it goes, what's my duty? It's 4. Okay, I'm going to make the waveform go high, and I'm going to count up until duty. 1, 2, 3, 4. It goes there. I've hit my duty period. I'll now transition the waveform to go low, and I'll count the rest. 5, 6, 7, 8, 9, 10. Then it resets everything and repeats. So we'll do another instance of that wave. Okay, so we get to configure what the duty and period is, and duty is generally going to be less than or equal to the period, because if I had a duty of 0, the output wave would always be low, and if my duty was equal to the period, the wave would always be high. And we can see that. You can actually put that into your configuration and you'll see that. So you can actually make it a high signal or a low signal with basically no waveform at all if you do that. Yeah, so that's part of what we want to do when we come up with a waveform. This allows us to do things like make a 50% duty cycle square wave if I make my duty 1/2 of the period. All right, so if my period was 10 and my duty was 5, it would make this a nice perfect 50% duty square wave. Okay. The values you pick for period and duty are kind of dependent on what kind of problem you're solving. If you are just making a fixed waveform, you would probably want to pick, well, you could pick any values for period and duty as long as they made the duty cycle that you were looking for, but they could be relatively low values. So if I knew I was trying to make a 40% duty waveform, I could use 4 and 10, that would be fine. If you want to modulate the output signal, meaning you want to change this duty and have quite a bit of authority over it or control over how big it is, we would typically shoot for a much higher period, because then the duty could be a much smaller fraction of it, and I'd have much more control over the width of that positive time or on time of that waveform. So I'm going to do that. I'm going to redo this, but I'm going to talk about it in terms of, say, a period of 200, and then we'll establish what the frequency will be, and then we can work through a problem based on that. So one of the things we'll find with 8-bit values is I'm quite restricted in what I can use for period and duty values because they have to be 8 bits or less, and they're unsigned values. So I'm going to pick a period of 200 for this example because it's even and it's relatively large. It fits into an 8-bit value, and I have then quite a bit of options for my duty, so I can go 1/200th is my resolution on how wide the positive part of that waveform could be. So if I was to read through the question says we want to generate this with a frequency of 2.5 kilohertz, for example. So we get that out of the problem. It will basically present itself, and this of course could also come in terms of time. So it would say the period of the waveform could be 400 microseconds, and of course period is 1 over frequency, and frequency is 1 over period. So if you are given one or those other pieces of information, you can easily convert it into the other form if that's what you need. Right, so in this case, what we're saying is the entire time of this output waveform would be 400 microseconds. Or if I were to look at this on your scope, we would see that that's running at 2.5 kilohertz. That's one full cycle of the output waveform that we're looking for. Now, if I have generated values and saying I want to use a period of 200, really what we're doing then is we need to divide this whole waveform up into 200 little chunks. Right? And then the duty would be a value that is less than or equal to 200, and it would describe what that would look like in terms of counts of that period. So if this is running at 400 microseconds for one full cycle, I need to configure the PWM clock so that it's actually 1/200th of that, because I'm really trying to find out what the time is of one of these little chunks, and there's 200 of them. So to figure that out, I would actually need to take 400 microseconds and divide that by 200, because that's the period I've chosen to use. And if we do the math on that, you will find out that this ends up being a pretty small value, right? This ends up being 2 microseconds. So each one of these little chunks is 200 microseconds, and that's actually going to be the period of the PWM clock. Period of PWM clock. Okay, so that's what we're trying to achieve here, and this is the thing that's overlooked usually when we configure the PWM, is that the period has a huge effect on how we divide down the bus clock to generate the PWM clock, because period has to be factored in. It's not always just the output period that we're looking for of the waveform. We have to factor in how the period is actually subdividing that up. And obviously if I used a period of 100, then the math would work out differently. So I've redrawn this out to kind of put this into perspective of how we'd set up the clocks. So again, we have figured out that this whole period of this has to be 400 microseconds or 2.5 kilohertz. So that came from the problem that we're trying to solve. And with a period of 200, we've discovered then that each little piece of this output waveform has to be 2 microseconds or running at 500 kilohertz. So ultimately, what we need then is the PWM clock to be running with this 2 microsecond time or 500 kilohertz frequency. And ultimately, that's sort of the goal that we're going to try to get coming out of the PWM. And the clock for the PWM has to be derived from our bus clock, which is running at 20 megahertz if you've used your PLL code. So that means each period of our bus clock is 50 nanoseconds. And you can work this out in terms of time, or you can work this out in terms of frequency. It probably depends on how the original problem was presented to you, but it's not really critical. You can switch between the two to use whatever's easiest for you. Okay, so in terms of what we're looking for then to clock down the bus rate, in the case of frequency, if I consider the main bus rate is 20 megahertz and I'm looking for a PWM clock rate of 500 kilohertz, if I were to divide that out, I would see that I'm looking for a total division of 40. And the same thing if I do this in terms of time. I know that my entire period for my output waveform chunk, so 1 period of my period is 2 microseconds. So if I divide that by the bus rate of 50 nanoseconds, then I get the same 40. So it doesn't matter which way you work this out, you should end up with the same value. So I'm looking for a total division of the bus clock of 40. Now the way the PWM module works is it has 2 values that you can plug in to provide that division that we're looking for. In general, we're going to use both of them, and you don't have to. You can actually choose to use either the first stage or the second stage, but we'll typically use the second stage, and the notes talk about that. Okay, so the first division step that we put in is a power of 2 division, which means that when I go and use this, I'm clocking down by 1, 2, 4, 8, 16, 32, 64, or 128. So this is a 3-bit power of 2 value that I could plug in. So it's only 3 bits, which means I have that range of 1 through 128 as a power of 2. So the second stage is any 8-bit value we want to plug in, and this value is multiplied by 2. And if you plug in a value of 0, that would be problematic, obviously. So the module views that as being full scale. So we generally won't put 0 in here. We'll put in some value, but the system multiplies the value by 2. And what we're trying to come up with then between these two scaling values that we're going to plug in is we want to bring that bus rate down to whatever we want our PWM clock rate to be, which is a value that we figured out by taking our total period and dividing it by the number of period counts that we want that we're going to plug into our period register. So we take the waveform period, which was given to us from the original problem, we divide it by the period count that we wish to use. This will give us the PWM clock, and we need to clock down then from our bus rate to give us our PWM clock. And we do it through these 2 stages. And effectively, these things are multiplied together to come up with a total division that we're going to be running the bus clock through. So we have some options here. We're looking for a total division of 40. So there's actually a couple of combinations here that would work. So the first stage being a 2 to the n, we could use 2 to the 0, we could use 2 to the 1, 2 to the 2, and we can try 2 to the 3. So this is going to give us values. 2 to the 0 would be divided by 1, 2 to the 1 would be divided by 2, 2 to the 2 would be divided by 4, and 2 to the 3 would be divided by 8. On the second stage, we can plug in whatever value we want as long as it's in the range of, say, 1 to 255. But that value is going to be internally multiplied by 2. So that just happens free of charge. So if I consider 2 to the 0 divided by 1, I would still then have 40 left over. So I could plug in 20 on the second stage, which is really 2 times 20, which would be 40. So 1 times 2 times 20 would be 40, which would give me total division of 40. Okay, the next one, if I were to use 2 to the 1 for the first stage, that would give me division by 2, which means there would be 20 left over. So I could use 2 times 10. So these are the values I'm actually plugging into the register, which would be 40. So 2 times 10 doubled, which is 20, would be 40. If I divide by 4, that would leave 10. So I could use the 2 times 5, would be 40. And in this case, this is going to be a problem, because if I use 8, I would really want to put 2.5 in here to do 2 times that to make it 5 times 8 to be 40, but obviously if I try to put that into the register, the 0.5 is going to get lost, and this won't be the value that I'm trying to put in. So if you end up with a fraction, obviously that won't work. So my options then for this were to use 0, 1, or 2, and the corresponding values that would work with that would be 20, 10, or 5, because remember, internally these are multiplied by 2. So 0 would be 2 to the 0, which would be 1, 2, or 4, which is what these actually end up being. So 1 times 20 times 2 would be 40, 2 times 20 would be 40, or 4 times 10 would be 40. And these are all values I can plug in. So remember, this is a 3-bit power of 2. And this is an 8-bit int that's multiplied by 2 internally. And from there, we can actually go and start plugging these things into the registers and see if we can actually generate this waveform. So when we go to put this in terms of code, we would make sure that we are in fact running at 20 megahertz, because that's pretty important, because all our clocking information is based on the bus running at 20 megahertz. And we want to use 200 counts of our period for the PWM. So from what we saw in the math, we need 2 microsecond units for our PWM clock, because 200 times 200 microseconds gives us the output period that we're looking for on the waveform that we got from the original problem. So again, if I divide my 2 microseconds, which I'm looking for in the PWM, by the bus rate of 50 nanoseconds, I have that total division of 40 that I'm looking for. And there's a few combinations, as we talked about, that would lead to that. And in the code, I'm going to use the 2 times 20 version, because it allows me to see both registers getting populated. Okay, so I want to do this on channel 7. So again, you would have to look in the notes at this. So if we were to bring those notes up, if I can find them. There they are. Channel 7 is a B group channel, and it isn't assigned to anything, so I can run this on the AD2 without having any problems of this turning on a LED or something. So I'll use channel 7 for this, but this would work for any channel. I just need to be aware this is a B group channel when I do this. Yeah, so I got to configure the B clocks to make this happen. So I would clear out the bits, for that upper nibble of PWM PR clock, so the prescale clock. I want to punch out the bits and then put back 1, because 2 to the 1 would be divided by 2. Yeah, so that's what I'm doing. So I've added 2 as my first division stage. Then when I get to configure clock SB, that would leave 20 left over. So I'd write 10 into the register, because I know the register value is going to be multiplied by 2 internally, which means this 10 becomes a 20. So I've got 20 then in this register effectively. That gets multiplied by the 2 from the previous stage, meaning 2 times 20 gives me a total division of 40. So I've set up the prescale and scaled clock, so clock B and S clock B, to be the total 40 that I'm looking for. I would then select that second clock, so the SB clock, for channel 7 by writing a 1 to PWM CLK in the appropriate bit, so channel 7. So that means it's using that second clock. I could just use the first scale, but I've chosen to use the second scale. And in the case that you can get the total division that you're looking for out of just the first clock, first stage, then you could use that and you don't need to worry about using the SB clock. But typically the notes will do this. Okay, so I would then go and configure the duty for channel 7 to be 200, so 200 counts of whatever my PWM clock is, in this case 2 microseconds. And the duty will be 50 times that 2 microseconds. So the waveform will start out high, count to 50, then go low, and then continue to count for 200 before it repeats everything. Okay, so I've enabled the channel with writing to PWME in the appropriate bit, and I've chosen to make the polarity high, so the waveform starts high and then goes low when the duty is reached, as described in 8.3.2.2 of Big Pink. So if I look at the output waveform from this when I run it, I will see that that's more or less exactly what I get. Because I know I'm starting high and then going low, I have configured the AD2 to trigger on a rising edge. So basically this rising edge would mean the start of my waveform, and it is got a positive width of about 100 microseconds, and the entire period is 400 microseconds as we calculated. And then the whole cycle repeats. And if I change my duty value, of course I'm changing this high time, and it can be anywhere then from 0 to 200, because that's what the period is. 0 would give me a complete flat line, 200 would make it always high, and everything else then would be a fraction of 200. Yeah, so hopefully that makes sense to you. If you have any questions, you can always contact me, and I will try to explain it further. Thanks.